Good afternoon, everyone. I hope you're doing very well. In this lecture, I'm going to be discussing about clock domain crossing, CDC design techniques. Those who are in VLSI design area or want to get into semiconductor industry, these are some basic things one needs to be familiar with. So let's try to understand what do we mean by clock domain crossing. As the name stands out, clock domain crossing. So we're gonna cross some signals from one clock domain to another clock domain. And these two clocks are not synchronous, asynchronous clocks with the different frequencies. So for example, in this diagram, we have clock domain CPU clock domain and GPU clock domain, and we are just passing one signal. Okay. Now, here in this diagram, we have just one flip-flop, synchronizing flip-flop in the receiving clock domain. Okay. Now, this is a typical example of clock domain crossing. Now, there is a problem with this one synchronizer. Okay. So, in typical design, VLSI SoC design, we basically transfer the data between flop to flop. Now, as long as both flops are in one clock domain, we are good. But as our signals are crossing the clock domains, we need to be very careful to properly tackle the issue. So let's say what's going to happen if we don't take care and we just pass from flop to flop. So this will act as a synchronizing flop in the receiving clock domain, but it's just one flop. So because of the inherent structure of flip-flops, the signals have to, the signal pulse width or toggling has to fulfill the criteria of setup time and hold time of flip-flops. Okay, if they don't fulfill the criteria, there is a tendency that this design will not work, simply because too many things are changing. And if you guys have taken basic course in digital design, the first fundamental they teach you that the flip-flop may go into unstable state. You don't know what is the output. We typically call it metastable state. Okay, so we have to basically enforce that that requirement of let's say, for example, this is my clock. Okay, now, so this is the clock edge, rising edge. So every flip-flop has a requirement that your data signal should be stable, okay, before the rising edge of the clock. So this is rising edge. The signal, data signal, should be stable. So this is, say, setup window. This window is setup window. And the signal also should be stable after the rising edge of the clock for certain time, which is depending upon the technology requirement, and we call it hold time. So separately, these called setup window and hold window. Okay, this is your rising edge, setup window, some small time, and hold window. And it has to be, it is must requirement to match the hold time requirement and setup time requirement. Hold time is really must, because if you're not matching the hold time, your chip is not going to work. Anyways, we're not going to go in detail how to do static timing analysis and all, But in this lecture, the idea or the aim of this lecture to give you familiarity with clock domain crossing, okay, and how we can tackle in the RTL design. So let's say these two clocks, clock CPU is asynchronous to clock GPU, and only one synchronizing flop we have here. Let's say this is a hypothetical clock CPU and clock GPU to clocks, and our data, which is the output of the flip-flop from the CPU clock AQ data, looks like this way. So after some time of the rising edge, data changes, and then again. Now what happens here, okay, if this is just one flip-flop, okay, and your clock GPU its period is not too much big, it's just slightly higher period than clock CPU, okay. So what's going to happen in that case? Most likely the data will be sampled, AQ data will be sampled in receiving clock domain, which is clock GPU, when it is changing, okay, because there are a couple of reasons here. The data width is too small, and it is just changing too early, and it is most likely getting into the setup window of the synchronizing flip-flop FFS, okay. Or in other words, we can simply say that the data is not stable when the clock is changing, or we already discussed that we have to maintain that requirement that data should not change in setup or hold window of the flip-flop, okay. So what's going to happen that the data output SQ1 data, it will be, so this flip-flop certainly will go into metastable state. So we don't know what is the output SQ1 data. It's invalid. We don't know really. But after one clock cycle, when the signal is stable, AQ data is stable, it will sample the correct signal and it will give you the proper output. But whether that output it sampled correct value or not, you don't know. We typically call that the flip-flop will enter into metastable state, okay. The result of that would be the invalid data will be propagated throughout the design, and your design is not going to work, okay. So what we can do, simply we can use a technique called two flip-flop synchronizer, okay. So what it is, basically we had one flip-flop already and we add one more flip-flop here, okay, just before using the data in the rest of the circuit, okay. So by doing that, what we did, we basically made sure that the data is stable. So one flip-flop is going to go into metastable state, but not the other flip-flop, okay. Now it depends that how fast is the data is changing, okay. If the data is changing too fast, we might have to consider adding one more flip-flop. That depends on different factors. So typically we call it something called Mtbf, mean time before failure. These calculations needs to be done for any signal which is crossing the clock domain boundary, CDC boundary. For any signal we have to do these calculations. Now in typical industrial environment, technology guys, they already have that information, they have already calculated. So as an RTL designer, you just simply ask with them. Nevertheless, as the theory stands, we should be, have some idea about what it is. So So in simple sense, the Mtbf is proportional to 1 over the clock frequency of the receiving clock domain and the data which this receiving clock domain is receiving, that means AQ data. So most of the time this is observed that if your data is changing too fast, you have increased probability of Mtbf, or very high speed design, your frequency is too high. So in those cases, what is a typical technique is that you use one more synchronizing flip-flop. Okay. Now, synchronizing flip-flop can be one more or two more depending upon different factors. So it's always best idea to check with your company's technology team that guys, we wanna use synchronizing flip-flops, or do you have inbuilt synchronizing circuit, special circuit for synchronization? So you just simply use that circuit. But nevertheless, how you can use three synchronizing flip-flops? The same way like you have done for two sync flip-flops, same way three sync flops. Okay, and that will make sure that your data is propagated correctly to the rest of the design. All right. Now let's say another interesting example. For example, you have synchronizing flip-flop, everything is fine, but from the sending clock domain, that is clock CPU, you have some combinatorial logic which you are not registering it. Okay, so what can happen in that case? Most of the time people will say, oh, I'm just synchronizing in the receiving clock domain, I don't have to do that. But no, this is not right, because what's going to happen here, let's say this is the D signal here. So D signal, that's a typical nature of combinatorial signal, that it might have glitches, or it will go up and down too quickly. So now these glitches will cause a problem. So these glitches will cause the flops in the receiving clock domain to go into the metastability state too often. So that increases the probability of failure. Okay. So the best idea is that to register or synchronize the signal from the sending clock domain to receiving clock domain. So what you need to do, that's a practice, good practice, that first synchronize the signal, which is this your D signal, with respect to the sending clock domain, and then send, and then again synchronize it. Okay, I'm sorry, I shouldn't say synchronize, I should say register it. So you are just registering the D signal, just register it in the sending clock domain and synchronize it in the receiving clock domain, and you are good to go. Okay, that circuit will work. All right. Now let's discuss another interesting thing. What are the typical problems when we pass too fast CDC pulse? Okay, so you have done everything right. You are registering the data signal in the sending clock domain, and then in the receiving clock domain you have two flip-flops synchronizing. However, your pulse or AQ data is changing too fast. Okay, so there are problems. Okay, what's going to happen that if your GPU clock or the clock domain 2 or receiving clock domain, its period or it's too fast, its pulse width or time period is not big enough, and the data is changing too fast, then it might happen that this AQ data is asserted and deasserted within one clock cycle of the receiving clock domain. Okay, this is not the right behavior. So you will never toggle the data in the receiving clock domain. That's just not okay. So one must have to be careful that what is the clock frequency of the sending clock domain and receiving clock domain, and what is the pulse width gonna be of the signal which is crossing the clock domain boundary. Okay, that's a people have done research and they found that when passing CDC signal between two clock domains through a two sync flip-flop structure, then the pulse width of the CDC signal should be 1.5 times at least the width of the receiving clock domain. What it means that your AQ data, it should be stable, it should not toggle enough till this point. That means that your whole one clock period and roughly one and a half clock period from here. Okay, 1.5. So this width basically, the pulse width of the AQ data. All right, remember that. Now, so as I said that the first solution is that simply you make sure that the CDC signal pulse width is 1.5 times the period of the receiving clock domain. Okay. Another way is the closed loop solution, where you send the feedback signal to the sending clock domain. How? Simple. That you synchronized and you get this output, and you take this signal and send it back, okay, in a loop as a feedback to sending clock domain, okay, and properly synchronize that feedback signal in the sending clock domain, which is clock CPU, and put some logic, develop a state machine or something to recognize that okay, the data is properly being captured in the receiving clock domain. Okay, so that is now there is the advantage and disadvantage of both techniques. So in the first technique, in the open loop solution, you know in advance that this much is the clock frequency of the receiving clock domain, and your CDC signal pulse width is 1.5 times. But what happens that if the technology change or something changes and designer forgets to update the design, which is based on open loop solution, then the design will fail. Now, closed loop solution has the advantage that it will never fail. However, it will be slower because, and also the added logic is simply because you're getting a feedback signal and then you're writing some extra logic. But nevertheless, it is the safest way. Closed loop solution is the most, how do I say, is the safest way to make sure that your signal is being properly captured in the receiving clock domain. Okay. Now let's talk about another important thing. So far we discussed about one signal, just one single bit signal going from one clock domain to another clock domain. But what if you have many signals, say data bus, or you have some sort of some sort of ready signal, enable signal, and bunch of other signals which are crossing one clock, crossing from the one clock to another clock. Okay, now this is important. You need to be very careful. So you can't just simply pass multiple signals and expect your design to work. No, it will not work. So always remember that only one signal needs to change, okay, in the clock domain crossing. If it is not so, then you need to use somehow some sort of enable logic or load logic to consolidate those multiple signals into one signal. Okay, so typical approach is what it is that like if you have say 3-4 signals, so all these 3-4 signals you consolidate those multi-bit CDC signals into one CDC signal, and then use the same approach. Register the signal in the receiving clock domain, and then send it, and then synchronize in the receiving clock domain. So from the sending clock domain you are registering, and in the receiving clock domain you are synchronizing. Now another approach would be that you can use a gray code. Okay, now for example, you have enable ready signal, now these signals will have possible values 0 0, 0 1, 1 0, 1 1. Okay, now what happens that you can use the binary to gray code converter. And then send the signal. Okay, now what happens with the gray code counter, that it makes sure that only one bit is changing across the boundary, only one bit at a time at one clock cycle. So you are safe, other signals are stable, only one signal is changing. Okay, so that's the beautiful technique if you have say multiple signals. There are other techniques where you can use FIFOs, asynchronous FIFOs and all. But I'm not going to go in detail into using the FIFOs. Now, another thing would be that you can use a synchronized load signal, okay, to safely pass multiple bits. So, for example, you want to send the data. Now, within the sending clock domain, you write some sort of logic that the data bits, you know, so these data bits, you receive these data bits in the receiving clock domain when you have some sort of enable signal or load signal. Let's say load signal. So you have generated a load signal along with this data bus. You can use some state machine, use some state machine logic or whatever logic you wanna write. Generate a load signal, register it, and then pass it to the receiving clock domain, and back to back flip-flop. Now once you have this signal, then it means that now you can use the data bus. Okay. However, it's always good practice to send a feedback signal back to the sending clock domain. Which makes sure that your data is being properly read. So always remember that only one signal, in a group of signals, only one signal should change in one clock when you are crossing from one clock domain to another clock domain. That is the basic, simple, fundamental rule need to remember, right? So thank you guys. I hope you guys have enjoyed this lecture, and do send me your feedback. You guys are sending me amazing feedback, liking video lectures. That's encouraging me to create more interesting stuff for you guys. And don't forget to subscribe LeProfesseur YouTube channel. Once again, thank you for subscribing, and have a wonderful day.